Greetings, higher level students. I made this video and I realized that I misspoke a little bit in the beginning. So I just want to add a quick disclaimer because I don't know how to add the text over which I made my mistake. It's a silly one. I want to correct it for the record. The slope is not the change in the x divided by the change in the y. It's actually the other way around. It's the rise over run. So it should be the change in the y divided by the change in the x. I was rewatching my edit. I didn't feel like going back and doing it all over again. And I was just listening to myself make this silly mistake over and over and over again. I apologize for that. So I'm just going to put this disclaimer out in the front. If you see any more mistakes, just point them out to me during class and we'll all have a big laugh. All right, so I apologize for that. Enjoy the video. Take care. All right, you absolute legends. We are now starting the next chapter. And this one is going to be on one of the most famous high school and undergraduate college math topics, and that is calculus. That's right, we are starting Calculus 1, and by the looks of it, they expect you to know quite a bit in order to be able to proceed through this chapter, a lot more than the standard level. And that's fine for higher level students such as yourselves. Okay, so briefly, I am going to just kind of introduce the sort of kind of concept, and then I'm going to illustrate it with a real life example. So here we got a curve, f of x is equal to e to the x power. And we have something called a secant line. A secant line is a really fancy way of saying a line that passes through the curve at exactly 2 points. And we are interested in knowing what is the slope of this line. All right, well, the slope of a line, also called the gradient of a line, we all know this from 8th grade. We've said it a billion times. It's just rise over run. And that's going to just be the change in the x divided by the change in the y. All right, not a big problem. Now, and obviously we can do this for anything. I mean, as long as these 2 points are different from each other, we could just say, okay, the change in the x divided by the change in the y, the change in the x divided by the change in the y. Now we want to ask one question. What happens when these 2 points overlap? All right, what is the slope of this line? This particular line has a special name, and we've said it a billion times. It's called the tangent line. And the tangent line is exactly a line that touches the curve at 1 point. So, very serious people have asked the question, what is the slope of the tangent line? Well, the slope of a line is still the slope of the line. It should just be, the change in the x divided by the change in the y. But we run into a real problem because what is the change in the x? Well, if it's the same point, then it's 0. And then what's the change in the y? Well, it's the same point, so that's 0. So the slope is going to be 0 divided by 0? Well, obviously not. I mean, as I move around here, it's clearly got a slope of some kind. So, but 0 divided by 0 just makes no sense. So how do we get around this problem? Obviously this presents us a real challenge, doesn't it? So, I mean, the secant line's not a problem, but so what do we do? Well, some really smart people just noticed that, hey, the secant line gets really, really, really close to the slope of the tangent line, right? I mean, even if we just move it apart a little bit, it's still pretty much the same. As long as these 2 points are really, really, really close to each other, it's pretty much the same thing. The difference here is like 0.02. It's pretty much exactly the same thing. As long as there's a little bit of a difference, then we've got the slope, right? And we could always make this we can always make the distance between these 2 points as arbitrarily small as we want. you know, and it'll get pretty close to the actual slope of the tangent line. But now we want to ask, well, okay, we're getting closer and closer and closer to zero, so that's fine. But what is the slope of the tangent line? Like, what is the point that we cannot pass? You know, like we can always get it closer and closer. So what is the actual limit here? What happens when the distance between them equals zero? What is the slope that we can't actually pass? And that will be the slope of the tangent line. And I say it that way on purpose because that's going to be exactly the definition of the first thing we're going to cover today. All right. Now, this probably just seems like really stupid stuff, but it has real world applications, and I'm going to illustrate that to you right now. All right, and to illustrate my point, I now present to you one of the most famous Olympic events of all time, and that would be when Usain Bolt set the current world record. So let's take a look at this. There's the start, and Bolt got a good one, and Gay's right with him, and so's a soft foul. Bailey's there too, but here's Bolt. Bolt charging to the front. Gay's coming, but can't catch him. Usain Bolt, look at the time, 9:58, world record. I told you, Tom Hammond, we were going to see a 9:5 tonight. Okay, so what did we just witness here? Well, we witnessed the world's fastest man, and you know, that's cool. But what if we were interested in knowing how fast was he going? Well, how do we actually measure speed? You know, it's not like I can just it's not like I can just know how fast he's going just by looking at it. I mean, if that were true, I'd be able to just look at this thing and say, okay, well, how fast is he going? At this particular frame, how fast is he going? Well, intuitively, we know that he is moving, right? In this particular frame, we know he's moving, and we know he's moving a bit faster than everyone else. But how do we actually go about calculating it? So if I were to just drop this on your desk, what would you do? You know he's moving, but you don't really know how to measure that, right? Well, the definition of speed is the change in the distance divided by the change in the time. So in order to measure speed, you absolutely are going to need two frames, at least two. So like this one and this one. So here you can see he's moving a little bit that much in about 1 second, you know. And from there, we should be able to do a pretty good estimate of how fast is he going, you know. Now, that's not fair because the the camera's also moving too, so it's not like we have a pretty good frame of reference here. But if we were to just watch this, you know, here he is. So the camera's moving. He's clearly moving really fast. But as you can see, we need two frames in order to measure speed. But the problem is, like, hey, we know that he was moving in this particular frame. We just want to know how fast. Well, now we can actually get a better estimate of how fast he's going if we can like slow it down, if we had more frames. So before, I think the distance between the two frames was something like 3 feet. Well, here now the change in the distance is just like a couple of inches, maybe, you know. So here we can get a much better estimate of, let's say, how fast is he going in this frame by getting just like a couple inches over. Like, all right, he moved a couple of inches in a fraction of a second. So now we have a really good estimate of his speed, but it still doesn't tell us exactly how fast is he going in this particular frame. We would need really good technology to get two pictures that are really close to each other in time. You know what I mean? But it's a real problem, and it's actually a problem that applies quite a lot in physics. It's not just sprinters. It could also be planetary objects moving through space, and we want to know their trajectory. We want to know their angular momentum, and sometimes we want to know if they're going to hit us. So using calculus, using this idea of the tangent line, is pretty useful. And this is just a real practical example of trying to figure out, well, okay, how fast is he going at this particular moment, you know, or whatever. So that's the idea behind calculus. Now we want to try to find a way to actually. Now we want to know. Okay, now that I have the practical application of it, what is the definition of the slope of a tangent line? You know, what is the definition of the slope of the tangent line? Well, in order to actually acquire this particular thing, we're going to need the idea of something called a limit. Now, a limit, what do you think of when you think of a limit? You think, all right, it's something that I can approach, but, I can't really pass. I can't really pass through this point. This is the point that I want to stop. I want to get up to, but not include this point. That's the idea of a limit. So a speed limit, if we were all being very legal, means we can get up to this particular speed, but we're not allowed to pass it. In this case, we're going to let the limit be the distance between these 2 points. And we want to say what is the slope of the line when the limit is 0? What happens when the distance between these 2 points is 0? Well, obviously we're not going to know the slope when the distance is actually 0. We're not going to be able to do that. But we can ask, what is the slope approaching when we get closer and closer to that limit? So here we know the slope. Here we know the slope. It's like having 2 frames on the Usain Bolt thing. Here we know the slope. Here we know the slope. Here we know the slope. And we can see that the slope of this line is quickly approaching 1 slope, isn't it? We can get closer and closer and closer and closer. And we can see that the slope is getting closer and closer to what value? That value is called the limit. That's the idea of a limit. And it allows us to get around the pesky problem of dividing by 0, which is a big no-no. All right? So I'm going to now give you the actual definition of the derivative, which is what that is. All right, now without further ado, we are actually going to introduce the idea of the slope of the tangent line. So here we got a plain old function, and I promise we will actually get to this particular function, which is e to the x. We're going to do that in the video today. But for now, let's choose an easier one. F of x is equal to x squared. And I want to know what is the slope of the tangent line when x is equal to, let's say, 2. All right. Well, in order to do that, I have to have the definition of the slope of the tangent line. Well, the definition of the slope of the tangent line is just, okay, we have to take the idea of a secant line, but we're going to say what is the slope of the secant line when the 2 points approach each other, basically. That's going to be the slope of the tangent line in a nutshell. Well, all right, so let's start by just saying m. M will be the slope of the tangent line for now. That'll be pretty simple. And what's the definition of m? What's the definition of the slope? It's just going to be y minus, y1 divided by x minus x1. Okay, that's the definition of the slope. Now y is just f of x, right? And more to the point, if we were to give this a little bit of distance here, if we let h be the distance between these 2 points, it becomes a lot easier to deal with. So if we just let this first y be this point over here, we'll let this one be f of x, and we'll let this one be f of x plus h. It's like h is just some distance, some height. So this will be f of x, and this will be f of x plus h. That makes more sense. So we'll let this y be f of x plus h. It'll be the point on the right, and this one will be the point on the left, just for simplicity's sake. So the top will be f of x plus h, and then minus f of x. Now this is the change in the y divided by the change in the x. All right. And the cool thing about doing it this way is that this point will be x, and this point will be x plus h. right? So one cool thing that happens when you do it this way is that the denominator actually gets a lot easier. So the first point will be, x plus h, and the second point will be x. So here's the change in the y divided by the change in the x, and oh look, x minus x. Those x's go away. So on the bottom, it's just going to be divided by h, which is nice. H is the distance between the 2 points, the horizontal distance between the 2 points. This is a perfectly good definition of the slope of the secant line. And what we want to know is, well, okay, what is the slope when we set the limit equal to 0? So like when the distance between the 2 points equals 0, what is that slope? So if I wanted to modify this a little bit to give me the slope of this tangent line, we would have to apply something like this. And I'm just going to go ahead and write this down. This is the actual calculus lingo. We say lim as, not x, this is supposed to be h. Sorry. The limit as h approaches 0, what's the slope? Okay? This is the actual thing that we want to use in order to discover what is the slope of the tangent line. So what is the slope of the secant line when we set the distance between the 2 points? If we said what's the limit of this, like what is the slope of the secant line as we make the distance closer and closer to 0? That's the idea of a limit in an intuitive nutshell. And as you can see, if we just set h equal to 0, we're going to have a real problem because we're dividing by 0. But here, it's kind of like a hack. We're saying, hey, let's just pretend that h is not 0. Let's pretend that h is really, really, really close to 0, but we're allowed to play around with it. Let's actually give ourselves permission to play around with it until we get the slope. This is the definition of the slope of the tangent line, which is great. It also has another name. It's called the derivative of f. And we denote this in lots of different ways. Dy dx is the most common way, I think. The derivative, and this little d kind of stands for difference. It's like a tiny difference. So the differences in the y divided by the differences in the x's. You can think of it like that. Alternatively, it's f prime of x. That's another way of representing it. It's probably my favorite way. F prime of x is the derivative of f. And it's the slope of this line at a particular point. Now, the original question that I ask is, what's the slope of x squared when x is equal to 2? Well, let's go ahead and use our cool formula and figure it out. All right, so if f of x is equal to x squared, then what is f prime of x going to equal? Well, it's going to be the limit as as h approaches 0. And what are we going to have on top? We are going to have x plus h squared minus x squared over h. So if I were to just plug this in, don't overthink it here. F of x plus h, that's this thing. It's just, I just plug, wherever I see an x, I'm going to stick an x plus h. That's it. Wherever I see an x, I'm going to stick an x plus h. And then f of x is just, well, x squared. So this is f of x. This is f of x plus h. That's it. And then h is just still on the bottom. Now, what do I do with this? Well, I got to do a little bit of algebra shenanigans, right? A little bit of algebra shenanigans, not a big deal. So I'm allowed to FOIL out the top. That seems like a valid move. So this will just be x squared plus 2xh plus h squared, right? So let's just scale this out a little bit here. So I just FOILed this thing out into that. And let's simplify the top a little bit. X squared minus x squared. All right, so those just go away. That's nice. Okay. Oh, that's a plus shouldn't be there. Cool. Nice, nice, nice. So the x squareds kind of cancel out. That's nice. Hey, there's an h here and there's an h here. I can factor that out, so that's cool. Why don't we go ahead and do that? I'm just doing a little bit of algebra. It's really nothing fancy. We all kind of know how to do that. So we got h 2x plus h on the top. So I just factored out an h. Hey, these h's cancel out. That's cool. So what do I got now? Yeah, I'm just doing a little bit of algebra. It's really not a big deal. And then 2x plus h. Nice. So what is the slope of this line when h approaches 0? Well, why don't we actually plug in 0 now? Before we could not actually plug in 0. If we plugged in 0, we would be dividing by 0. But now we say what happens when h approaches 0? Well, okay, this is just going to approach 2x. And that's it. That's the answer. The slope of the derivative of x squared is just going to be 2x, which means that what is the slope of the tangent line at, let's say, 2? Well, you plug in 2 here. So the slope of the tangent line at 2 will be 2 times 2, which is 4. So the slope of the tangent line at 2 is just going to be 4. This is the formal definition of what's called a derivative. The derivative is just the slope of the tangent line at a particular x value. That's it. All right. Let's do a couple more worked examples now. All right, now let's move on. Before we go on to some of the cool rules we're going to be applying to calculus, I want to do one more using this definition of a limit, because you're never going to see anything this hard on the IB exam or any exam in here in particular. So this is really a college level problem. And that is, I want you to find the derivative of this using the formal definition of a limit. Okay, now you will not need to do this at the high school level. You're going to have a different technique, which we're going to go over in this video, which is a lot easier. But I want you to know how to do this because when you go to Calculus 1, your freshman level class, they're going to expect you to know how to do this. So here's the definition of a limit applied to x to the 1/3 power. So this is f of x plus h, and this minus f of x all over h. And you may have noticed from the last problem, the way that we handle a problem like this is we want to try to cancel this h out with an h on the top. So somehow we need to factor an h out of here. Well, I'm going to go ahead and tell you, the way that you handle this numerator is you need to apply an algebraic identity, which many math professors are going to assume that you know. Obviously, I don't expect you to know these. Even I have to look this up. So I'm like, all right, something cubed minus, like a cubed minus b cubed. I happen to remember that there was a special identity with that. So I went on to Google and I'm like, okay, where is it? And it's this one right here, number 7. It's a cubed minus b cubed is equal to a minus b times a squared plus b squared plus ab. All right, so I want to use this identity. Why do I want to use this identity? Well, I'm going to let a equal the first one, and I'm going to let b equal the second one. And what happens is if this is a minus b, which this is a minus b, and I multiply it by a squared plus b squared plus ab, I'm going to get a cubed minus b cubed, which is nice because what does that mean? It means that these 1/3 go away. You know, a to the 1/3 power to the 3rd power, well, it's a power to a power. It's going to cancel this exponent out, and it's going to become x plus h. Again, I want to reiterate, you don't need to know this for the high school level, but you will need to know how to do this when you go to college next year. So this is just helping you get ready for the next level, okay? So I want to find a way to have this a minus b. I want to multiply it by a squared plus b squared plus ab. I want to multiply the top by this. Well, in order to do that, I need to do my special operation. I'm going to multiply it by 1. So it's going to be this, which is a squared plus b squared plus ab where we let a equal x plus h to the 1/3 power and b equal x to the 1/3 power. Cool. So a squared. So instead of a to the x plus h to the 1/3 power, it's x plus h to the 2/3 power. That's what happens when you square it. You double the exponent, so 1/3 becomes 2/3. Same thing here, and then this. Okay, well, because I'm using my algebraic identity, I'm cool. I could actually just rewrite this as a cubed minus b cubed now, which is just going to be x plus h minus x. See? That's nice. So now it's x minus x, and it's just h times this huge mess on the bottom. So x minus x, that goes away. And hey, look, the h's cancel out. So I'm left now with 1 over this huge mess. At this point, I am allowed to let h equal 0, so I'm going to plug 0 into that. I'll plug 0 into that, and we're going to get this. So this is x to the 2/3 power plus x to the 2/3 power plus x to the 2/3 power. So this would be 1 over 3 times x to the 2/3 power, which I'm going to go ahead and write this in a friendlier format, 1/3 times x to the negative 2/3 power. That's it. And this is absolutely the right answer. All right. Yeah, so that's just a really special example. You're going to want to know how to do this exact process for your Calculus 1 course when you go to college. There is a special rule we're going to be going over called the power rule, and you're going to be abusing this a lot. We're going to be practicing this quite a bit in class as well. All right, so let's move on to the next part of the video. All right, and without further ado, we're going to give you your very first calculus rule, which is the most basic one, and it's one that you're going to get very familiar with in this class. It is called the power rule. All right, now I don't know if you noticed that there was a weird pattern with the last two examples, but there was actually a pattern, and it follows this exactly. If f of x is equal to x to the n power, then the derivative, quite simply, is n times x to the n minus 1 power. And it doesn't matter if n is a fraction, or if it's a negative number, or if it's a whole number, or whatever. You just subtract 1, you bring the exponent down out front, and you subtract 1 from the exponent. That's it. So that means that if you have, x squared as your function, okay, well, that's just going to become 2x. Whoa. Yeah, x squared is just going to become 2x. That's it. What if I had x to the 4th power? Well, that's just going to become 4x cubed. Eventually you get really quick at doing these. The 4 comes down, then you subtract 1 from the exponent. This is something they're going to definitely expect you to know how to do at the high school level. All right, now what happens if you've got something really wacky, like, I don't know, 1 over x cubed? All right, whoa. That means I can't use the power rule, right? Wrong. Okay, you can. You just need to write this in a calculus-friendly format. This is actually x to the negative 3rd power. This one, again, you can use the power rule. It doesn't matter what this exponent is. It could be a negative number, it could be a whole number, it doesn't matter. So what you're going to get is just negative 3x to the minus 4 power. You just subtract 1 from negative 3, you bring the negative 3 down out front, and that's it. What happens if you have a fraction? I think we kind of already see where this is going. What if you have, let's say the cube root of x, right? We just did this one in class. We just did this one in class. It's really not hard. Okay, so the 1/3 is going to come down out front. Doesn't matter what it is, and then it's going to be x to the negative 2/3 power. Isn't that a lot easier than having to do that huge definition? You know, 1/3 minus 1 is just going to be negative 2 over 3. See what I'm saying? Right. What if you have something really, really, really wacky? Here, I see this one as number 3. Let's say like 4t minus 8 over the square root. Come on, spell square root of t. All right, all we got to do is write this in a calculus-friendly format. Instead of x, they're doing t. We're obviously allowed to do derivatives of whatever variable letter we want. Doesn't matter. And here we also have an example of two different functions. The derivative is just going to apply to each one individually. So the derivative of the first one is just going to be 4. Now what about this one over here? Okay. All right, so before I actually take the derivative, let's actually write this second one in a calculus-friendly format. This will be 4t minus 8 times t to the negative 1/2 power. Every time you see a radical, you can write that as like to the 1/2 power. And if you have anything in the denominator, you can pass it through to the other side and change the sign. I don't know if you all remember doing that last year at all, but that's the law of exponent. We are definitely allowed to do all of that. Now when we take the derivative of that, this 4t is just going to become a 4. It's still the power rule. It's t to the 1 power. So the 1 comes down, then 1 minus 1 is 0, and anything to the 0 power is just 1. Basically, the t goes away when you take the derivative. All right, so let's just write that down. The first one here is just going to become a 4. And now the second one, all right, simple. The negative 1/2 is going to come down out front. Negative 8 times negative 1/2 is actually a positive 4. And this is going to be t to the negative 3 over 2 power. Because negative 1/2 minus 1 is negative 3 over 2. And that's it. Okay, so the negative 1/2 comes out front. Negative 8 times negative 1/2, a negative times a negative is a positive, and 8 times a half is 4. And negative 1/2 minus 1 is negative 3 over 2. I mean, really, the power rule can just be applied all over the place, no problem. All right? That's the definition of the derivative. It's called the power rule, and we're going to be practicing this a lot. The n comes down out front, and you subtract 1 from the exponent, boom. That is the derivative of a polynomial. And that's it. So you'll get started on the homework and have no problem with that.